Good morning, everyone, and welcome to our webinar. We are going to give people a few more seconds as they funnel in, and we'll begin shortly. In the meantime, hi, Dor. How are you doing today?
All good. Hi, Felipe. Good morning. Me and the monster want to say hi, and let's begin. Probably our audience want to hear the content.
Yeah, no, definitely. But just so you know, I've got a larger monster than you. Although I know you have an even real size monster in the office. Unfortunately, it's not featured today. But yeah, no, definitely. Let's get started. So, hi everyone, and welcome. Thanks so much for being here today. Before I get started, I'd like to quickly review a couple of housekeeping items. We welcome your questions. Please use the Q&A button located at the bottom of your screen to ask your questions. And remember, you can enter them at any time during this webinar. You don't have to wait until the end, all right? Also, please note that today's webinar is being recorded, and we are going to email you with a link to the recording and the slides following the event. We push quick poll questions where we are asking, how often do you scale your database services? So plenty of options for you to choose from, and irrespective of your answers here, we do believe that the content we'll be bringing here today to you is going to be very valuable for you to rethink your existing database topology as well as management. All right? So thank you so much for your responses, and let's get started. So welcome everyone. My name is Felipe, and I work at ScyllaDB as a solution architect for a little bit over 3 years now. I love puppies. I am an open source enthusiast, and I am, of course, a ScyllaDB passionate. Along with me, guys, please meet Dor Laor, CEO and co-founder of ScyllaDB. So Dor, thank you so much for being here today. Why don't you just go ahead and please introduce yourself?
Thanks, I'm Dor. I report to Felipe, and I also love snowboard, as you can see in the back. All right, let's go. Can you move to the next one?
Yeah, sure.
So why ScyllaDB? Probably you know the answer if you joined. If you haven't, you may learn during this webinar. We'll talk about new innovation at Scylla. Scylla is a performant and scalable database. We believe that it has the best high availability and disaster recovery in the industry because we copied ideas and algorithms from existing databases and just made them better. We also don't have lock-in, and it's open source and enterprise and as a service, and have compatibility with Cassandra and Dynamo. And if you happen to configure Scylla, other than your IP address and your credentials, then probably something is wrong, because we try everything to be automatically tuned and to have the performance go out of the box. So let's dive in. And don't take my word for it. We have plenty of other users who try it in production. Not just try, but actually use and depend their mission critical workloads. Next slide.
Yeah, that's true. Just a reminder that all those users have shared their histories in ScyllaDB Summit, right? So if the audience is curious about what they're using ScyllaDB for, they can always access our website. So agenda, Dor, what have you prepared for us today?
Not just me, but so today we'll speak about Scylla 6.0 and elasticity. So that's the agenda. First, why we speak about that. Isn't Scylla elastic enough? The value proposition of 6.0, it's really like just a couple of minutes, and then the main thing would be a demo by Felipe, and then we'll explain the theory behind the demo. That's the main things. Let's jump as quick as possible to the demo. So just to answer, wasn't ScyllaDB good enough before? ScyllaDB version before 6.0 were really good. In this one, we present how we can scale across all of the instance sizes by AWS every time we double the instance size, we also double the amount of data, and we can load double the amount of data the same amount of time. So we scale linearly. Next slide. Also, we continuously test Scylla and test the latency with Scylla once while we change the topology, while we add node, remove node, abuse nodes, fail node, repair node, backup nodes. We make sure that the P99 latency remains under 10 milliseconds, even under node operations. So Scylla has been always good with that respect. But there are things that we improved at 6.0. Next slide. So what are the problems we wanted to address? The main issue was the architecture. We adopted the eventual consistent architecture, both in the data plane and also in the control plane, the metadata. Now, it's really convenient to have eventually consistent metadata, because you can scale without a single master. So we can be very scalable. We can have very scalable clusters that span hundreds and even thousands of nodes. Be partition tolerant, so you can have multiple data centers and they can get partitioned, and all partitions can function in parallel. And the database is very distributed this way. But it also has a flip side and a downside, because we do need to be consistent with our metadata decisions, especially how we organize the data within all of those, across all of those nodes. So that's why we only allowed topology changes, meaning adding and removing nodes, only once at a time. Now, if you have a very big cluster and you need to add, let's say, 30 nodes, 50 nodes, you only can do that one every time, and also wait 30 seconds between each of those changes to make sure that it's really only one at a time. And if you have a failed node, you must need to recover that node before you continue to add other nodes. So that serializes the whole process, and it's a problem. On top of that, we had some other problem. It's more of implementation details, that the streaming time to send data to new joining nodes was dependent on the schema. We parsed partition by partition, and if you had small partition, it took more time than we wanted. And lastly, there are other operations like cleanup, and I'll address specifically cleanup later, that you had to require to run on every node after you scale the cluster, and they took time as well. So with 6.0, we're fixing all of this by moving from eventually consistent to immediate consistent, assisted by Raft, and another implementation of tablets, which we'll demonstrate. So that's 6.0, and the value proposition, last slide before the demo, is the following. First, elasticity, so things get parallel and fast. It's super fast to add a node to a cluster. Once a node is being added to the cluster, that node can immediately process requests. So even though only subset of the data that it's supposed to host arrive to that node, it can immediately serve requests related to that piece of data. And Felipe will shortly demonstrate them. And we can add many nodes at parallel, like 30 nodes at parallel at once, no more sequential addition. Obviously, it influences speed. We solve the streaming of SS tables. We copy files now. That's actually more in the enterprise version. But we also have load balancing, so we can split the key ranges in the cluster among nodes dynamically. It's not related to the topology. Also, in the tablet architecture, and it's not the first time we talk about it, then a table starts with very few tablets and expands over time. So initially, you may even, if you won't hint us at all, we'll start with a single tablet. And if you have usually tablet is up to 5 gigabytes in size. So if you have a small tables, and many times some tables are gigantic, can hold a petabyte, but many small like assistant tables may only have 5 gigabytes. So if you have such a table, it will be hosted only by a single node plus the replication, and even a single shard, a single vCPU inside. It will make scans and all of the operations very fast. Everything is also simple. You can add nodes, but these nodes may not have data ownership yet. So we decouple topology changes from data ownership, the opposite from the situation we had before 6.0. Some operations are transparent, like cleanups, and soon repair. And the last one is TCO. Tablets will allow you, and elasticity will allow you to shrink the free space. So you wouldn't need up to 50% of free space in the cluster. You'll be able to run in up to 90% utilization. That's a big cost reduction. And also, you wouldn't need to be over-provisioned. If things are not as elastic as they should, then you need to have enough spare capacity to accommodate big spikes. But if everything is very elastic, then you can run thinly provisioned only what you need and just grow the cluster if you need to. So that's it. Let's go to you, Felipe.
Thanks, Dor. I wish one day I will be a good presenter just as you are. And so, all right, let's actually see how all those values actually manifest in practice. So, Dor, welcome to our demo. And what you can see on my screen is basically a small 3-node cluster actually running some traffic. And the cluster is currently running on top of I4I X large instances in AWS. And we can see that each node is doing roughly 16,000, almost 17,000 operations per second. So if we hover in the overall to see the overall system load, we can see that the system load is about 50%. So this is our initial state. Tablets are enabled, and we can see that each node, looking over here in tablets per instance, each node holds 32 tablets each. Next, what I will do basically is to switch to my terminal, and what I want to do basically is to run the first Ansible playbook that I have prepared for us today. And what this playbook basically does is it's going to start ScyllaDB, and then it's going to wait for the SQL port readiness, which means that we are going, that's the moment when clients will be able to connect to the cluster. So without further ado, let's simply run this playbook, and let's see exactly what happens. The good thing about using Ansible here is that it quickly highlights some of the major changes ScyllaDB introduced and that Dor just spoke about. The first thing I want you to pay attention to is that we are bootstrapping all nodes in parallel. In other words, unlike other databases in previous releases where you would need to scale in a serial way, as Dor was speaking, now everything can be done in parallel. And the second aspect we can see relates to how quickly newly added nodes can start servicing requests. The process completes really quickly, and nodes can start serving traffic immediately to help with increasing demand. In fact, it completes so quickly that it took me longer to speak than the actual process to run. So what we'll be doing next is to get back to our monitoring, and let's see what's happening under the hood. So look at that. Thanks to the new tablets dashboard, we can observe migrations happening in real time. So in this tablet over time per instance, we can see the nodes which recently joined the cluster is starting with 0 tablets. And what happens next is that the existing nodes, our original 3 ones we had when we started this demo, we will start migrating their tablets to the new replicas. Therefore, the dark brownish tiles represent the existing nodes migrating tablets, and the white, light orange and nodes we will start getting darker, which means that they are starting to receive data from our previous nodes. So over time, the system will get into perfect balance, and all colors should match. In addition to that, we can look into this panel here in the bottom, and we can observe that the 3 nodes we recently added, they are almost halfway through the process of joining the cluster. Another thing we can and should do relates to performance. Dor spoke about latency as part of the value. So while all this process is running, we can see that latencies are pretty much under control. The new nodes which are joining, they are of course joining with a cold cache. So read latencies can increase a bit, but after the cache gets hot, they will eventually subside. And now, if we take a look here into tablets over time, per instance, we can see that this process is pretty much complete. And look at that. All nodes in the cluster already have the same tablet count, which means that pretty much the migration, the scale out is completed. So we can see that nodes start servicing traffic, and eventually the traffic will converge, right? This is for a request served from the application. And on the other panels, on the replica side, eventually the traffic will also converge, with writes and reads working differently. Because again, remember, for reads, ScyllaDB has its own cache, and the new nodes which as they bootstrap, they come up with a cold cache, and it may take some time for the cache to get hot. All right.
Yeah,
so
we have this heat-based load balancing algorithm. So we direct reads to nodes that has warmer cache. So those are the original nodes. Over time, everything will be even, but basically, this doubling the cluster was finished in how long was it? Like a 3-minute-ish?
It started here. 3 minutes-ish, 3-4 minutes.
Okay, this is how much data you've got there?
We've got roughly 150 gigs per node. Yeah.
That's not little, but not much for Scylla. But we wanted to demo it quickly. So if you have more data, then it will take some more time. But it's super quick.
Yeah, and I think, Dor, the main value is this, right? You can add as many nodes as you'd like to, and on top of that, we can say that those nodes will start servicing requests. So irrespective of your data size, you can simply scale your cluster, and while it's scaling, you should be able to service more demand as your application requires. So cool. As you can see, it was super fast, and the process completed quickly enough. But that's not all. So what I want to do next is basically I will get back to my terminal, and I will run the second Ansible playbook I've prepared for us today, which is this one, 2XL scale. This one is going to do the very same thing as the previous one, but the difference here is that rather than adding 3 nodes of the same size, we will add 3 nodes of a larger instance type, which is in this case, we are using the I4I 2 extra large which has double the CPU, memory, and storage capacity compared to our original node type. This is important because sometimes just doubling your capacity may not be enough. Sometimes you might want to scale your cluster by 4x, 10x. So this part of our demo demonstrates that ScyllaDB scaling is flexible to your needs. And as you can see, the same process just run on my screen. And of course, I mean, since we are quadrupling the cluster size now, Dor, what I'm going to do is basically I'm going to scale our clients because we have 4 times the original capacity. So we should be able to also service more traffic. And if we get back to the monitoring, we can see that once again, the process will repeat, right? So, but here's an interesting question. Since those 3 nodes we are adding, they have double the size of the original ones in the cluster, how will tablets and traffic get balanced in this case? I guess that's what we want to see, because into my intuition at least says if I'm adding nodes of double the capacity of another, then this node which has larger the capacity should be servicing twice as much traffic than the smaller ones, right? And we can see here that while the migration is going on, those nodes which joined are already started to service traffic, right? And what I want to see now, Dor, while this is running, is let's take a look into the streaming speed, right? So I switched to the advanced dashboard, and we have actually this streaming section on I/O where we can see how much traffic each instance is doing. It's a lot.
Nice to
Yeah.
it's a gigabyte a second per node.
Per
It's nice
node.
you can find it so quickly within our multiple dashboards and multiple graphs within every dashboard. It's nice.
Thank you. And I typically say that practice leads to perfection. But yeah, and I mean, we can also see it on the OS metrics if we are only interested in the NIC traffic, right? This is going to be here, yeah. But this also includes the traffic from the application. But yeah, I mean, if we take a look, I mean, 300 megabytes for the larger instance types, and this is for receive traffic, RX. So those are probably the nodes which just joined it, and those are the nodes sending traffic, right? Yeah, we can see there are basically 6 here. So yeah, that's pretty much that. It's super fast. And all right, let's see how our migration is doing. So yeah, cool. It looks like everything is finished. Yeah. So we can see that the smaller nodes, each one got 90 tablets each, and the larger nodes, they have 14. But we can see here that what's more interesting is that if we take a look into the request served, we can see that the 3 larger replicas we added, they are serving more traffic, almost the double, not exactly the double because the tablet count's not yet fully balanced, but almost the double than the smaller instance types. And this is super cool because it shows that ScyllaDB is able to easily balance traffic according to the size of your clusters. All right.
Felipe, I bet the audience asks themselves, did we configure anything to make bigger nodes have more tablets and more capacity, or Scylla figured this out on its own?
From the management perspective, I have done nothing. I basically added nodes and just like you would regularly do in previous ScyllaDB deployments. So no change from an user perspective. But yeah, there have been many coding changes in ScyllaDB internally to make it happen. I'm super excited about it.
Yeah, obviously, it's just amazing to see it at work. And and it's like completely fresh, out of production, out of release engineering. We're
Yep.
super pleased to see this, and the whole intention with different node types and node sizes is that you can also get it wrong. The initial sizing today doesn't matter. Like whatever you started with, like instance family X, instance family Y, you can quickly adopt to another instance family and maybe use instance family with a bigger density or a smaller density and optimize the instance size for your needs.
Yeah, that's correct. And remember, we scaled our application while we were adding those larger instances. There we go. We've got over 100,000 operations per second. This is super light traffic. I mean, remember when we started, our load was about 50%. So it could, and we should add even more load to get back to the 50%. So easily we can see that this cluster now should be able to do 200,000, even 300,000 operations per second with ease. The cluster is very, very light. And if we get back to the latency, look at that. Writes are sub-millisecond, and for most of the time, reads are also sub-millisecond. That's beautiful to see. And Dor, what I want you to do next, and basically for us to wrap up this demo is, what about removing nodes, right? After all, we added, we also scaled it, added nodes of a different instance type. So what if I am happy with just those two extra large instances we added? Yeah.
Will you remove them in parallel too?
Of course, let's do it in parallel. And then let's see how ScyllaDB is going to behave. So I'm going to run this Ansible downscale playbook. And yeah, I mean, we are scaling in. And what you're going to do is basically to decommission nodes in parallel. So if you are familiar with Ansible, you know that it is going to run commands simultaneously, unless you configured it to do things in a serial way. But now with this new ScyllaDB release, you don't really have to. So if we take a look into by instance, basically what's going to happen here is the opposite process. So now the nodes which are already part of the cluster, they are going to start losing tablets, or in other words, they're going to migrate off tablets from them to other existing replicas which are going to remain in the cluster. And then once this process completes, then the full migration is will also be the full downscale is also going to be complete. And we can already see.
Just can you please update Grafana for 5 seconds interval and not 30?
Yeah, I'm sorry.
The audience at home asked me.
Yeah. Yeah, that's cool. That's a nice catch, Dor, because yeah, one node already left the cluster. So, but yeah, I mean, if we were going to wait 30 seconds, we would be missing tons of updates. Now, each node is going to be leaving the cluster on its own pace. And this is what I really wanted to share. This is going to be repeated for each node. And if we have time near the end, I believe we can get back to here to my screen to see how it happens. But as you can see, it's super fast. I mean, as I'm speaking, nodes are losing tablets, and you can see it really happening live here. Probably the next one which is going to leave is this green one. Yeah, that's the one. See, it's now down to only 3 tablets. Then it's going to get to 0, and then the other nodes will follow. All right, that's what I wanted to show. There, should we get back to the presentation?
Yeah, just nodes are supposed to give away tablets in parallel. The one that is left without no tablets will eventually get decommissioned. So that's like runs in parallel and until decommission completely ends.
It's beautiful to see. And just while you're speaking, that node just left. So, and the other one is in progress. Yeah. Super fast.
Music to my ears. Well, thanks for the demo, Felipe. Let's jump back to the slides. I'll share my screen. Yeah.
Okay.
Okay, demo time ended. Let's speak about the theory behind tablets and Raft and how we could get to the situation where we're now. So we talked about being eventually consistent before. We had to implement a consensus mechanism. So we implemented the Raft algorithm. It's implemented in a special way because it's being run by all of our nodes and all of our shards. It's more complicated than a standard implementation. Raft is an algorithm, but in general, to synchronize a state machine and make it consistent across multiple sets of machines. And whatever you send to all of those machines through the Raft protocol is supposed to be consistent with others. So we send, among other things, we also started to send schema updates, and we also send token metadata across all the nodes. And once we send them, we also issue read barriers. So the nodes in the cluster that are aware of the topology, they make sure that they wouldn't answer to read and write requests if they're not part of the cluster. So we have these barriers. So sometimes over topology changes, a node used to own a token range. It may lose a token range and still get queried by clients about that token range, but it wouldn't answer because there was a read barrier after topology has changed. So we do this, this process is called either read barrier or fencing, where we signed the topology with a version number and a UUID, and nodes refuse to answer if the topology version is not the most up-to-date. So this happens under the hood. Nothing changed in the client, still the CQL protocol, but under the hood with the metadata management and the RPC, the customer RPC, everything is managed on your behalf. Another major improvement we've done recently is to linearize the schema versions and also to use a UUID in order to enumerate the schema, because the schema is now sequential. It's being linearized as if it's sequential, and it's not a forest of schema changes we had before. So only the most up-to-date schema matters, and we add the UUID, so it's really trivial to figure out whether you have the latest schema or not. It makes schema changes fast, especially if you have a big cluster. It takes much less CPU and much less processing to gather the latest and greatest schema. Now, so Raft is one gigantic change. The other one is tablets. We weren't the first ones to implement tablets to a database. I actually searched Google in order to figure out who was the first, and I discovered that our ancients used clay in order to clay tablets in order to write the rules and write their data. Someone who wrote an article called it a database. So they were the first, and later, a long time afterwards, Bigtable came along, and they split the data based on tablets as well. Recently, we adopt their implementation is not exactly the same, but the principle is pretty much the same, to split the big table into multiple smaller chunks, where you can dynamically allocate those smaller chunks to nodes and make them independent of the topology and the nodes. In order to get here, we went through multiple releases in the past couple of years, and now we graduate with the first tablet-based version. More to come, but this is the first version that has all of the pieces of the puzzle there in implementation. So right now we have the new metadata. It's a table of tablets, of the tablet ownership of the data, and the tablet ownership has lists of token ranges and a tablets that owns them, and the replica list of for every tablet ownership, and to make sure that we have this mapping. So when a query comes along, we can figure out to which nodes we need to route this query. It's all managed by Raft, this table. It's a system table, automatically managed on your behalf. You have nothing to do with it, but you can browse it and read it through. And the data itself within every tablet, the tablet is full self-sufficient. So every tablet has its own main table per table and its own SS tables, and it's managed as a whole. If we so this is one happy log structured merge tree of each tablet. If we want to send a tablet from one CPU shard to another, or from one node to another, we just need to send all of those SS table files, and the tablet will be migrated as a unit. So it's relevantly simple to grow and shrink back. This is part of the game, or the mechanism that supports the fast elasticity. So before with vnodes, then we had more of a static way to figure out which keys reside on which nodes. There was still key ranges that mapped to nodes, but there was no tablet table as before. And we had to do the load distribution once you add a node, but you couldn't do it dynamically over the node lifetime, only when you added or removed nodes. So dynamically, but not that elastic. Today with Raft, we have this Raft tablets table managed by Raft, and the system, the coordinator, checks in the Raft table to figure out which node it needs to route to. This is how the table looks like. On the right-hand side, this is a standard system table. You can see the table ID and the last token as the primary key. And we have other things like the list of replicas every tablet has, and plenty of other fields, whether this is in transition because tablets are supposed to be quite dynamic. This table is automatically replicated by Raft to all of the nodes in the system, and it's all kept consistent. So tablet balancing is relatively simple. We need to send the entire tablet, a set of SS tables, to another CPU or another node, and boom, we balanced it. We have a load balancer. This is a load balancer is basically a code being run by only a single node. It's still maintained by Raft, and once this node dies, then someone else get elected as the load balancer, and continue from the previous state. All of the state is synchronized by Raft, and the load balancer collects statistics about utilization, about volume utilization, CPU utilization, get topology commands, and also maintenance commands, and it fits which tablets need to run which process at a given point. So for example, over a single period of time, you wouldn't want to run both repair and backup and migration to a tablet, but you can run it over multiple tablets. Tablets is small, it's only 5 gigabyte in size. A decent size cluster should have thousands and tens of thousands of tablets, and all of them can be being processed in parallel. while every major operation should only undergo a single tablet at any given point of time. There are lots of operations which are really trivial, like resharding. Resharding is, let's say, if you want to change the same server which previously had 4 virtual CPUs in only two virtual CPUs. Maybe you like to contribute 2 of the virtual CPUs to some other things. So this is the process called resharding. And if you do it in this direction, basically it's just no need even to copy files, just the system needs to know that it has more files of the other tablets to process. That's it, just a logical operation, no copies whatsoever. If it's the other way around, we'll need to split an existing tablet to 2. Also, that's relevantly simple. It's usually being done by compaction. Cleanup is also a trivial operation. You need to run a cleanup after you contributed a range of keys. Let's say we added a node, so every node contributed a range of keys to that remote node. And if you still have those range of keys, pre 6.0, we had to delete them immediately and to run cleanup because there's no enough consistency and there's no I'm looking for that word that prevents you of accessing the data that you do not own, like we have today, and you had to delete it. Otherwise, you'll get that data being accessed by a node that doesn't owns it. And with these days, it doesn't happen, but you still want to clean up afterwards, so to just delete data. So we automatically clean afterwards with tablets. It wasn't the situation with vNodes. And we just need to delete the old files. That's it. And Scylla does it automatically. So that's a big improvement, both in simplicity, but also in times. Cleanup with vNodes can take sometimes hours, depending on the schema. And now it's trivial and transparent. Another improvement is streaming. So previously, when we streamed, we used to process one partition at every time. And if the partition was really small, let's say 100-byte partition, then we had to process all of those. And this took processing time. Now we just send those SS-stable files to the remote nodes without any processing because they're being sent as a whole tablet. So that can be up to 30 times faster. Driver support. So we modified the drivers to support tablets. It's okay to still run unmodified drivers because even drivers that we modified to be tablet aware, initially they just go without awareness and go to a random node in the cluster that serves as the coordinator, and the coordinator will just route the request to the right node by checking the tablet version. In parallel, asynchronously, there's a request token to figure out what's the tablet placement that get notified to the client. We didn't want to send all of the tablet table to the client ahead of time because this table can be quite big, tens of thousands of tablets, and if you have a lot of connection, maybe it's too much. So clients learn as they go, and that's why you can also use an older client. And another improvement, not related to tablets, but related to Raft, we've been adding more and more services to Raft in order to enjoy from its consistency. So we recently added authentication and service level to Raft. For example, authentication, that's important. Like previously, you always had to manage authentication on your own and make sure that the authentication table is replicated enough. And if you remove existing nodes with authentication, you had to fill them manually. Now with 6.0, nothing to know about it. It's a Raft table. It's being sent automatically across all nodes, so nothing to be concerned about, and no denial of service if a node with authentication information is down. So super simple. So this is it. This is the content of 6.0. We have Raft with consistent schema, schema-based UUID, so fast schema changes. We have topology changes, parallelism, elasticity, tablets, fast streaming, and also Raft tables like authentication, for example. Did I miss anything, Felipe?
Sorry. No, I don't think you have. I think I am the one who have missed it, because in the demo we used the ScyllaDB Enterprise streaming you were mentioning. So yeah, that was going to be my only addendum. I think it's perfect. Cool stuff.
So let's see what's coming. First, just for completeness, so tablets and Raft are enabled by default with Scylla 6.0. There are some additional features that weren't yet adjusted to tablets, like CDC and LWT encounters. So this is coming. Soon we'll finish this up in the upcoming open source versions. And don't worry, if you have tables without that needs features that are not fully tablet enabled yet, you can continue to use vNode. So we haven't canceled vNode. We are targeting to cancel vNode eventually because they don't have any other benefit. What's coming beyond that? Number one, we'd like to automate repair. So instead of controlling repair and running repair is a full scan operation, so it can be complicated and also needs a load balancer. Since tablets has a load balancer already, then we like to use it to simplify repair. We also will automatically use the GC grace period, which we already have in previous releases. So repair will be like super smooth and simple to use. Beyond this, we're about to make everything fully automated based on the mechanisms we have already. And Philippe, this says what's coming, but actually it's already there. You can, with your own management, you can do it. It's more coming to Scylla Cloud, where you will be able to start with an instance family like i3en, and dynamically move to i4i if you happen to have more throughput and less storage, or do the opposite, or move from a bigger node to smaller node, and vice versa. So no more complicated ahead of time sizing. You can do it always online. It's super fast, and you can get to line rate of all of the nodes, not just one node at line rate, all nodes at line rate. And basically you're limitless. So we'll try to move as fast as possible with Scylla Cloud and bring all of these advantages to you. These advantages can also come up to play in Kubernetes, so not necessarily Scylla Cloud only. So all of these mechanisms exist today. Beyond this, we have plenty of more algorithms. I rather not describe them for a couple of reasons. I hate to overpromise, and I do not want to hint the competition. But what we've got is already impressive. But more things are coming since the base becomes much better now with the consistency and elasticity. We can do a lot of things more that we couldn't have done before. So there's a lot to expect.
Yeah, I think that's perfect, Dor. Thank you so much. Do you mind if I steal your screen share for a second? Because we promised it to the audience that if we had enough time, we would show the how long it took for the nodes to live. And yeah, there it is. So 1, 2, 3, 4, 5, 6 nodes left to the cluster. And it took what, roughly 7 minutes. It started pretty much here in 18 minutes and then ended here in 25. So yeah, uh, roughly 7 to 8 minutes. And yeah, I mean, this is, as I said, it's pretty much the opposite process. And as each node starts living, traffic starts being balanced to the replicas that remain in the cluster. And that's it. We basically completed the entire demo, right? Anything you'd like to see more here, there, or comment?
It's well. I wanted to say that I checked the graphs and I thought, why don't we kind of lose them not one at a time, but faster together? But overall, 7 minutes, I have nothing to complain. But in general, like we'll improve our load balancer. There is plenty of room to improve it. But what we've got is amazing. 7 minutes to get rid of 6 nodes with data
Yep.
under load. Fantastic.
Yep.
I couldn't wish for a better release. So 6.0, there's definitely, go ahead and test it. It's there.
Yeah, no, definitely. It totally makes sense. Thanks for your feedback, Dor. And I mean, all that said, guys, I think this poll is really fair. How long does it take for you to scale your existing database? So please let us know in your answers. I can see many people are already answering very interesting answers. So thanks for that. And given that, guys, this brings us to the end of our webinar. Don't hesitate, as Dor said, keep on learning. Get your hands on ScyllaDB 6.0, play with it, try to run the very same steps we have done, and so you can see for yourself how it works. If you'd like to learn more about the internals of our technology, please visit our blogs for more on ScyllaDB engineering cool stuff. And also, late in October this year, we'll be hosting P99Conf. Dor Laor himself will be a speaker there. And if you have never attended P99Conf, it's basically the conference for all teams' performance. All right? Anything you'd like to say on P99Conf there?
I'm waiting for your memcache replacement presentation at the next P99.
Yeah, that was supposed to be a surprise, but now, yes, I will be featuring on P99Conf as well. And I guess that's it, Dor. Thank you so much for agreeing to do this. Thank you so much for being here. For the audience, if you'd like to learn more or discuss more about ScyllaDB, please visit the forum.scylladb.com. You can also engage us through Slack or through our social media. If you'd like to see the ScyllaDB code, remember it's open source. You can also find us on GitHub. All right, Dor, once again, thank you so much. Thanks for all the audience, and we hope to see you next time.
Let's meet you at the kitchen for beer or a
Yeah,
virtual
let's
beer.
definitely do that. Yeah.